Hello and welcome back. Today we'll be making every single logic gate using ladder logic, and we're going to start with the NOT gate. We're going to get right into it, but before we do so, why don't you smash like and subscribe. So as we can see in the truth table here, the NOT gate is an inverting circuit. If we take our input A, then our output X will be the opposite. So if A is 0, X is 1, and vice versa. And that's represented by this expression down here, X equals A bar. The bar indicates the NOT operation. Now to make a NOT gate in ladder logic is very simple. You just take a normally closed contact that represents your input, and you connect that directly to your output coil. This way, when your A input is de-energized at 0 volts, this normally closed contact will also be de-energized and stay in its closed state. Our positive signal on the left is able to make it through our normally closed contact and energize our X output coil. Only when you switch our A input to a positive signal, I'm using 5 volts for example, then our A input will become energized and it will switch states. So this normally closed contact will actually open up. This way we lose a path for our signal to make it to our output, and our output turns off when we energize our A input. So that's how you make a NOT gate using ladder logic. And we'll move on now to the AND gate. So to make an AND gate in ladder logic, you need to put 2 normally open contacts in series with each other, feeding the output. Each of the normally open contacts represents one of your inputs. The truth table for the AND gate says that our output X will only be true if our input A is true and if our input B is also true. If either of the one inputs is false, then we will not get a high output. And the expression that represents this is X is equal to AB. The multiplication represents the AND function, because anything times 0 is equal to 0. So the only way we could get a high output would be to have 1 times 1. If we have both of our inputs tied to a low signal, then both of our contacts will be de-energized. This means that they will stay in their normally open state, and we won't be able to get a signal through to the output. So our output will be low. If we energize our A input by giving it a high signal, the normally open contact will become closed and allow a signal to pass through. But because our B input is still de-energized, its contact will still be in its normally open state, and we will not be able to get a signal through to our output, and it will be off. And you can see the same thing happens if we energize only B and leave A de-energized. Our B contact will become closed, but since we have an open in our series circuit here, there's no way for a signal to make it through. The only way to turn on the output is to energize both of our inputs. This way, both of our contacts will become closed, and the signal will make it to our output coil, and X will become true. So all an AND gate is a series combination. We could have as many elements as we wanted to in series, and the output would never be energized unless all of them became true. Now we can get started with the OR gate. In ladder logic, the OR gate is 2 normally open contacts in parallel, feeding the output. You can see by the truth table, the output will be energized if you energize either one of the contacts. The output will only be off if both of our inputs are also off. The OR function is represented by the addition sign. A OR B is represented by A plus B. And so in Boolean algebra, 1 plus 1 equals 1, because we can only have 2 states. So you can see now, with both of our inputs pulled low, both of our normally open contacts will be de-energized, and so it's impossible for the signal to get through to the output in either branch. If we energize only our A input, then our A contact will energize as well and become closed. This way, we can see it doesn't matter what B is, because we have a direct path through to the output via A's closed contact. If we de-energize A and energize B, our A contact will return to its normally open state, and our B contact will become closed. This will be the same as the previous scenario, where our signal can make it through one of the 2 branches and make it to our output. So in this scenario, our output will be high. And if we energize both of our inputs, then both of our contacts will become closed, and our output will still be on, the same as it was when we only had one of our contacts energized. So this normally open set of contacts makes our output turn on if one input or the other becomes energized, and also if they both are energized at the same time. The only way for the output to be off is for both contacts to be de-energized when both of our inputs are low. Then we have no path for the signal to get through. Now we'll move on to the NAND gate. So here is the simplest way to make the NAND function using ladder logic. You put your variables in parallel and you make them normally closed, i.e. negated. This will give us the NAND truth table on the left, and because the NAND function is the opposite of the AND function, it will always be on unless both of your inputs are energized, in which case it will be off. So the expression for the NAND function is x is equal to a and b over bar, but you can use something in Boolean algebra called the De Morgan's theorem, where you can change the operation from and to or, and vice versa, if you split or merge the overbar. So in this case, we're changing the and operation into an or operation, and we are doing this to simplify our ladder logic. And that's the De Morgan's theorem. So we can see if both of our inputs are de-energized, then both of our contacts will be closed because we made normally closed contacts. This way the signal can make it through either one of the branches and our output will be on. If we energize our A input, our normally closed contact will become energized and open up, but since our B input is still de-energized, the signal has a path to turn our output on. If instead we only energize the B input, our B contact will become energized and open up, but because our A input is de-energized, the signal can carry through this top branch and turn the output on. The only way to turn off the NAND gate is to supply a high signal to both of its inputs. This will open up both of our normally closed contacts, and then our signal has no possible way of reaching the output, and it will be off. And one cool thing about this logic is that the NAND function is a universal logic gate. This means that we can use the NAND function to create every single other type of logic gate if we connect the NAND gates in the correct way. That will be a video of its own, so for now we'll move on to the NOR gate. So here is the simplest way to make the NOR function using ladder logic. You can see we have two normally closed contacts in series feeding the output, each contact representing one of our inputs. And because the NOR function is the opposite of the OR function, we can say that its output will only be on when both of its inputs are off. If either of the inputs turns on, the output will be de-energized. And here is the expression for NOR. We have A or B over bar, but just like we did with the NAND gate, we can use the De Morgan's theorem. We can cut this over bar and change the operation from OR to AND and say that this is also equal to A bar and B bar. If we use this expression of NOR, it makes our ladder logic simplified. So if both of our inputs are de-energized, that means both of our normally closed contacts will be closed because they're also de-energized. This way, our output will be on because we have a straight path. If we energize our A input, the normally closed A contact will open up. This will break the series circuit, and there's no path to turn the output on, so it will be 0. And the same will happen if we energize only the B input. Our B contact will become energized and open up, making it impossible for a signal to get through the series circuit to the output. And if we energize both of our inputs, both of our normally closed contacts will be open, and there will still be no way for the output to turn on. So the only way for the NOR function to output a 1 is if you make both of the inputs 0. Because in this logic, this is the only time when both contacts are closed and give us a path to the output. And just like the NAND function, the NOR function is also a universal logic gate, meaning if you connect your NOR gates accordingly, you can make every other type of logic gate. But that's a topic for another video, so we'll move on to the exclusive OR gate. So here's how you can make the exclusive OR gate using ladder logic. We have these two contacts on the left that represent A and not A, and we have these two contacts on the right that represent B and not B. And this A contact in series with this negated B contact represents our term A, B bar. It's an AND gate with A in series with not B. This is in parallel with not A and B, which represents the OR function for the two parallel branches, and the AND function here for this branch. And you'll find that this logic gate is similar to the OR gate, with the exception that when both inputs are high, the output will actually go back low again. The exclusive OR gate only gives you a high output if only one of your inputs is high. So it's known as a difference detector. We can see that in the de-energized state, when both inputs are off, there is no path for the input to go to the output. A signal cannot get past this normally open A contact, and it also cannot get past this normally open B contact. If we apply a high signal at our A input, we will energize both of these A contacts, and so the normally open contact will become closed, and the normally closed contact will become open. This will allow our signal to get through the top branch and turn on the output. If we then de-energize our A input and energize our B input, all of our contacts will switch states. This way our signal can still get through the bottom branch. And if we set our A input high as well, its contacts will flip, and there will again be no complete path for the signal to get to the output. So this is how you can make an exclusive OR gate using ladder logic and turn on the output only if one of the inputs is on. And so now we can move on to the final logic gate, which is the exclusive NOR gate. And here is what the exclusive NOR gate looks like in ladder logic. The exclusive NOR gate is the opposite of the exclusive OR gate. It outputs a 1 only if its inputs are the same. If its inputs are different, it will output a 0. And this is why it's known as a similarity detector. You can see down here is the formula for the exclusive NOR operation. The first term is A and B, which is represented by this normally open A contact in series with this normally open B contact. The second term is A bar and B bar, which is represented by this bottom branch with two normally closed contacts in series. The branches are in parallel due to the OR operation. In the de-energized state, where both of our inputs are low, our signal can come straight through the bottom branch because of our normally closed A and B contacts. If we energize our A input, both of our A contacts will switch states, and both of the branches will not allow a path for our signal to get through. If we switch both of our inputs so that A is low and B is high, all of our contacts will switch states, and we'll have the same condition where each path is blocked at some point and our signal will not be able to get through. If we energize our A input one more time so that both of our inputs are on, our A contacts will switch states and the signal can travel through the top branch and enable the output. So you can see how to make the exclusive NOR gate using ladder logic and how to turn on the output only when you have two similar inputs. And this is actually the last logic gate, so we've actually covered every single logic gate. So if you had a couple 5-pin relays laying around, or if you were just programming in this language, then you would be able to program anything you want because we have all the logic gates. So I hope you enjoyed the video. Please like and subscribe, and we'll see you on the next one.